Welcome back to my lectures on groups, rings, and fields. Our next topic is Sylow theorems. We've been learning the structure of a non-abelian groups using series of groups, and Sylow's theorems are going to give some more important information about finite groups, especially useful in studying non-abelian groups. So let us start with our known theorem, Lagrange's theorem. Lagrange's theorem is if H is a subgroup, if H is a subgroup of a finite group G, then the order of H divides the order of G. But we have seen that the converse of this theorem is not always true, especially when the group is a non-abelian group. For an abelian group, this converse is always true. The converse statement of this theorem would be if G is a finite group and D is a divisor of the order of G, then there exists a subgroup of order D. Let us state this theorem. This is not always true. The converse of this theorem would be, let G be a finite group and D divides the order of G, then there exists a subgroup of order D. This is not always true. This is the converse statement of Lagrange's theorem. This converse will be true for if G is an abelian group, always. But we have seen an example of non-abelian group where the converse is not true. So the counter example is A4 is alternating group of elements 4. It's a group of even permutation with 4 elements. Group is a group of order 12. And we have seen that there exists no subgroup of A4 with order 6. The point here we need to note is that A4 is a non-abelian group. That is one thing. The second thing is this divisor 6 has got 2 distinct primes as factors. 6 is equal to 2 times 3. 2 distinct primes as factors of this. So our next attempt is that what type of divisor of G which can be an order of a subgroup of See here, if you take A4, we can definitely find a subgroup of order 2 and order 3. But we cannot find an order of 6. But what is the generalization of this? What is the condition that we can put on the divisor so that you can always find a subgroup of that order? So that is our first step of this Sylow's theorems. So before we come to the main theorems, main Sylow's theorem, I want to recall a couple of results that we have established in group actions. So the results which we are going to use in this chapter are let X be a G set and X belongs to X. Then Gx is equal to the index of G over Gx. And when G is finite, then Gx divides the order of G. So this Gx and this Gx are different. This is the isotropy subgroup of G, and this is the index number of cosets of this subgroup over G. This is the size of the orbit. Gx is defined as elements from X such that there exists a G in G such that Y is equal to Gx. Or in other words, X is related to Y. That is Gx. G subscript X is elements from G such that Gx is equal to X. This is isotropy subgroup of G. And this is orbit containing X. If you remember, we have defined a D4 set with points and sides and vertices of a square. Then the orbits of the G sets are 1, 2, 3, 4, S1, S2, S3, S4, D1, D2, M1, M2, then C, then P1, P2, P3, and P4. These are the orbits. So G2 here is 1, 2, 3, 4. So the order of G2 or the size of G2 is 4. That is what I meant here. That is one result. The second result is Burnside lemma. Burnside formula. Let X be a finite G set and G is finite. Then if R is the number of orbits in X, then R times the order of G is equal to sigma G belongs to X order of G belongs to G order of XG. This XG is defined as elements from X such that Gx is equal to X. This is Burnside lemma. So we are going to use both of these results for our further results on finite groups. See, in both of these results, we didn't say what kind of group is G. It could be any group. Doesn't need to be a abelian group. It could be a non-abelian group also. So let us start with a sub-result. Let G be a finite group of order p to the power of n, where p is a prime. And from here onwards, if I don't say that p is a prime, we are assuming that p is always prime. Okay. So this in the whole the rest of the section, we are going to use the letter p for a prime number. So G is a finite group of order p to the power of n, and X is a finite G set. Then the number of elements in X is congruent to the number of one element orbits mod p. This is Xg is defined as elements from X such that Gx equal to X for all G in G. So this means that it is an orbit that has got one element. In our D4 set, xg contains only the point C. So this is the result we are going to show. Okay. So the proof is not that very complicated. Let us start with the number of orbits. Proof. Let R be the number of orbits in X, and let S be the number of one element orbit, an orbit that contains only one element, like here it is C. So that means xg is equal to S. Then let x1 dash dash xr be a set that contains one element from each orbit. For example, here the orbits are 1, 2, 3, 4, S1, S2, S3, S4, D1, D2, M1, M2, C, P1, P2, P3 and P4. Here R is equal to 6 and S is equal to 1. 1, 2, 3, 4, 5, 6. This x1, x2, x3, xr is something like this. Pick one element from each orbit. S1, D1, M1, C and P1. This is what I am talking about here. So X is equal to sigma I is equal to 1 to R G xi. Gxi is the orbit that contains xi. And these orbits are all disjoint. And the total number of elements is the total number of elements in X. Now we are reordering this x1 s dash and xr in such a way that all these s elements comes first. So we can write it like this. This is equal to rearranging the elements. We'll say that xg, this contains xg is the one element orbits, and there are s such elements plus sigma s plus 1 to r gxi. From the, this is a very important result, you should remember this. From the previous results on group actions, we know that each of gxi's divides the order of g, because g is finite and x is finite, and that implies gxi divides p to the power of n, because the order of g is p to the power of n. So from this equation, x minus xg is equal to sigma s plus 1 to r gxi, and this is a multiple of p, and that implies x is congruent to xg mod. Now let us define a special group called P groups. A group G is called a P group if every element of G, if the order of every element of G is p to the power of n for some integer n. Every element of G has an order of the form p to the power of n. Next definition is a subgroup of G is a P group if the subgroup itself is a P group. So we are going to use this P group throughout this section. We need a couple of theorems before we come to the main Sylow theorem. The first sub-result which you are going to show is Cauchy's theorem. Cauchy's theorem. Let G be a finite group and P is a prime that divides the order of G, then there exists an element A in G such that a to the power of p is equal to e. In other words, there exists a subgroup of order p of G. So, proof. What we are going to do is, we are going to construct a set with elements from G. So let X be P tuples of the form G1 comma G2 dash dash GP such that G1 times G2 times dash dash GP is equal to E, and that is X is equal to G1 comma G2 dash dash GP G1 times GP is equal to E. which we can write it as if this is equal to E, then GP is the inverse of the product of G1 dash 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 GP minus 1. So it will be like this: G1 comma G2 dash dash GP minus 1 comma G1 times dash dash GP minus 1 inverse over GI belongs to G. Instead of saying like this, you are writing the n-tuple like this. And that implies the number of elements in X. So you take any p minus 1 element from G. It could be a repetition. Okay. Then the last element is last coordinate of this tuple depends on the previous tuple. So this is actually equal to the order of G to the power of p minus 1. And that implies P divides order of X. Okay. Now let us consider a permutation 1, 2, 3 dash dash P in SP. This means 1, 2 dash dash P, 2, 3, 4 dash dash 1. That is this. And we call it as sigma. So sigma to the power of P is equal to the identity element of SP. Or in other words, the order of the subgroup generated by sigma is P. Now, this is a group. So we are going to define an action of this on X. So define an action of the subgroup on X by sigma of G1 dash 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 GP is equal to G1 G sigma 1 comma G sigma 2 comma dash dash G sigma of P. And that is equal to G2 G3 dash dash GP minus 1 G1. Because sigma 1 is 2, sigma 2 is 3, dash dash sigma P is 1. This also belongs to X because GP well, this is GP. This is GP and P1. GP and P1. So GP is equal to or you can say because G1 of G2 dash dash Gp is equal to E, and that implies G1 is equal to G2 dash dash Gp inverse. So inverse commutes each other. So this means that G2 dash dash Gp times G1 is equal to E, and that implies G2 dash dash Gp comma G1 belongs to X. So this is a well-defined action. So this definition of action is valid. So X is a sigma set, and that implies with the previous result X is congruent to X sigma mod P. But P divides the order of X. P divides order of X. P divides order of X. So this implies P divides X E, X sigma. Now X sigma is not empty. X sigma is not empty because E comma dash dash E belongs to X sigma. The elements of this are elements from X that are fixed by every element of this permutation subgroup. So there exists some other elements here. So X this is equal to X belongs to X such that rho of X is equal to X for all rho in the subgroup. This is what? This is actually our G1 dash dash Gp. So this is actually rho of G1 dash dash Gp. This is possible only when, see, for every row in the subgroup should fix X. That means this will be of the form A dash dash A such that A to the power of P is equal to E. You cannot take every A because it may not even be in X. So A comma dash dash A belongs to X such that A to the power of P is equal to E. Well, we don't want to write like this because if it's right like this, we don't need to do this. So this is the way it should be, where A belongs to G and A to the power of P is equal to E. This condition guarantees that this element is in X. Because we are taking, the reason why we are taking all elements equal, because every element of this subgroup should fix X. So that means there exists an element A different from E because P divides the order of this set. So there is another element here such that A to the power of P is equal to, and that is what we want to prove. There is one more sub-result we want to prove before the main Sylow theorem, and this result is based on the theorem which we just now proved. A finite group G is a P group if and only if the order of G is equal to P to the power of n for some n. So there are two parts here. Proof. Let G be a P group. And that implies every element of G has an order of P to the power of m for some m. So let us assume that let Q different from P divides G. And that implies Q a prime number, okay? And that implies by Cauchy's theorem there exists a element in G such that element, let us say G, let's say G to the power of Q is equal to E. And that contradicts the fact that G is a P group. If G is a P group, then we cannot have an element of order Q other than P. And that implies the order of G should be, meaning there is no other prime factor other than P for the order of G. Now next part is let G is equal to P to the power of n. And that implies every element of G has an order of some power of P by Lagrange's theorem. Because Lagrange's theorem states that every subgroup, the order of every subgroup should divide the order of G. So every element of G should have some power of P because the order of G is P to the power of n. If there is an element other than whose power is other than P, then this will not be true. So that is the proof.